There we go. All right, now I've started the recording. All right, so we were just talking, it's the very beginning of class, we were just talking about the homework, which is this document has the homework in it. You can access this document from this homework button right here. And then textbook is where you find the homework problems themselves. These are the assigned ones. Now let's review how it is that you actually submit your homework. Well, it's a self-reported grade. So you do this yourself on your own time whenever you want. You go into assessments and go to the homework quizzes. These are not real quizzes. I'm just using the quiz function of D2L. And what you're going to do is you're going to get in there. I'm just going to preview it for you so you can see what it looks like. There we go, preview. Right, you get in here, you start the quiz, but then all you're doing is just reporting your own score. So if you did 70% of the homework problems for chapter 1, then you would select true, 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 all the way up until I completed at least 70%. And then you can either select false for the remaining ones, or you can just leave them blank. That's fine. And then you submit this quiz. We have 3 unanswered questions. You say that's fine, submit it, and then it gives you 70%. So this is a self-reported grade, and you also put it into the grade book like this, okay? Basically, the way I set it up is each true-false question, the correct answer is true, so you get a point for answering true, and then you miss it if you answer false. But you all know that. It's not like you know, this is just a mechanism for you to put your own grade in the grade book. So you're on the honor system, so please be honest. Remember that you can repeat these homework quizzes over and over again as many times. There's no limit to the number of times you can repeat it, and there's no deadline. So basically, you just make sure you stay on top of the homework, and I want you to have submitted a homework grade, maybe not your final homework grade for chapter 1, but a homework grade for chapter 1 by the date listed on the schedule, which is the 29th of January. Okay. If later in the semester you go back and do more chapter 1 homework, then you can update your own grade. You don't even have to talk to me about it. You can just do it. How do you know if you got the homework questions right? Good question. For the odd problems, there are answers in the back of the book. For the even problems, you can ask your classmates or you can ask me. That would be a great thing to come to office hours and ask about. Okay. Now, I forgot to post the week 2 announcement. I will still do that. Okay, I'll put up a schedule and stuff for week 2. But if you are wondering what is happening, don't forget that you can look at the entire schedule for the semester over here on the syllabus. So just click on that syllabus link over there and scroll down, and you can see, aha, week 2. It looks like we're studying 1.4, 5, and 6 this week. There's no assignments due. There will be an exercise set due next week, and that exercise set is now available, by the way. But it's not imminent. So if you I'll show you where to find that. If you go into exercises here, you can find the second exercise set there and start working on it, though I don't expect you'll be able to finish it until next week. Okay. Okay. Any questions on this sort of bookkeeping stuff? I hope not to make a habit of doing this every single class, because usually we're going to dive right into talking about stuff. First thing I want to do now over on our whiteboard is just give you a little bit of broad feedback on what I saw after looking over your exercise set 1. And the main thing I want to talk about here is P implies Q. Any implication statement, any implication statement, if you want to if this is your original implication statement, there are various things related to this, connected to this, I'll say. There is the converse. I'm going to review this vocabulary. Converse, which is Q implies P. There's the inverse, which is not P implies not Q. And there's the contrapositive, which is not Q implies not P. So this, by the way, these two are equivalent. The original statement, P implies Q, and the contrapositive are equivalent to each other. That's one of the reasons I asked you to find the contrapositive of this type of statement on your exercise set. Okay, but then there's another thing that's important, which is the negation. How do you negate P implies Q? Okay. It is not this. It's not this, or it's not this. Okay, none of those are the negation. The negation is a separate thing. Note, the negation is not the same as any of those. Yes, that's all I want to say. Okay, I think the most common mistake was to write the inverse instead. So when attempting to negate, what was the one I gave you? Like, if we work together, then we will succeed. I heard a lot of, if we don't work together, then we won't succeed. That's not the negation. That's the inverse. How do you negate P implies Q? Well, the first thing to do is to rewrite P implies Q as something other than implication. And the way to do that is using the conditional disjunctive equivalence. You want to use the conditional disjunctive equivalence right here to write it as not P or Q, like that, right? Then you can say, oh, okay, well, if I'm negating not P or Q, then what I need to do is apply something else. Do you remember what we apply next? What's the next thing called?
Double negation.
Double negation is skipping a little bit ahead.
Or it'd be distribution, then double negation.
So there is a step before we get to double negation. Ibrahim's got it in the chat over here. I see. De Morgan's law is what we want to apply. So De Morgan's law is the thing that says there's two De Morgan's laws, one for negating an or and the other for negating an and. And excuse me, something caught in my throat there. And for negating an or statement, we see that the or becomes an and when you negate, and then the negation, which was here, let's make it like orange here. This negation here gets sort of distributed, but the or becomes an and, right? It's not just distributing, right? It's not like distributing, because when you distribute, you don't change. Like when you distribute one operation over the other, the operation in the middle doesn't change. But when you distribute negation, you apply De Morgan's law and the operation switches. So that's then we can apply here. I'll just cite De Morgan there. Then we can apply double negation here to cancel this out, and we get P and not Q. Double negative or double negate. Yeah, so there we go. So the answer to the question, how do we find the negation of an implication is like that. Now, Ibrahim also asked a question in the chat. I saw converse, inverse, and contrapositive are things that just apply to implication statements. It doesn't make sense to talk about like the converse of a disjunction, like an or statement. You can't have, or the converse of an and doesn't make sense. We just do converse, inverse, contrapositive for for implications. Negation is something you can apply to literally any proposition, and this is just the way you do it for implications in particular. Okay, so that is something I just really wanted to make sure I cleared up all of that stuff that I just went over, because that's probably where I saw the most mistakes in the exercise I just critiqued. Bilal, go ahead.
So I was gonna ask, is that the only way that you can find a negation? Because while I was watching those videos over and over again, I saw that if we find the truth table and we just find a value that's false, we can make like a statement. For example, if P then Q, the only time it's false is when P is true and Q is false.
Mm-hmm.
So isn't that the same thing as P and not Q?
It is. Yep. That's
so
exactly.
Then why do we have to do all these rules of equivalence and what's not?
Oh, good question. You don't have to. You don't have to. This is one way. This is one possible way to connect the dots, or arrive at this as the negation of P implies Q. But the other way to do it is with the truth table, just like you said.
Yeah, because I felt like it was just much more faster than this. I don't know.
It's different ways. It's different approaches to the same idea. Yeah. So if the truth table feels better to you, then that's fine. That's cool. Truth tables are generally considered to be not as efficient as applying like logical equivalences, because when you have, so like obviously in this case there's only 2 variables, the truth table is very small, there's only 4 rows. But if you had like 10 variables, then you'd have a huge truth table, and trying to come up with, trying to just manipulate algebraic, manipulate logical expressions by like just looking at the truth table and trying to extract information from the truth table would be kind of inefficient because it would be so big. That makes sense?
Yeah, and then I had another question about vacuous truths.
Sure.
So are vacuous truths, are they only for implication, or?
Yeah, vacuous truth really just arrives when, just shows up when you have this.
It works for biconditional as well, right? Or
yeah, I guess so. Yeah, it does. It does come up in biconditional, because biconditional involves implication.
Mm-hmm.
So yeah, that P implies Q is true whenever P, the hypothesis, is false. Yeah. So one of the ways that you can satisfy if and only if biconditional satisfy that is to have P and Q both be false, and then both implications in both directions, both the one way and its converse the other way, they're both vacuously true. So yeah, that's another case that shows up. Mm-hmm. Okay. Great questions, folks. If you are interested in some of this stuff about efficiency, if you're interested in like the efficiency of circuits, some of these concepts like apply to that, like the ways, like how you manipulate algebraic expressions to maybe, I keep on saying algebraic expressions. These are, I guess, logical proposition expressions, but they're very similar to algebra. And in fact, another way to view this is through the lens of something called Boolean algebra, where you write logical expressions like this using X, Y, Z plus multiplication, like addition and multiplication, basically take the place of or and respectively. And you end up basically, I mean, essentially this is actually algebra. It is a form of algebra. It's not the type of algebra that you do in an algebra class or a calculus class, but it is still algebra. And if you are really interested in that, there is one of the possible project topics you can do is on Boolean algebra and the tools that we use to like minimize circuits and make computers more efficient, like that kind of thing. So anyway, just wanted to put that out there so you know that that is a possible topic you can look into later this semester. All right, so we got to start our next subject. Section 1.4 introduces predicates and quantifiers. So we have been doing propositional logic. We need to expand our perspective to what's called predicate logic. Okay, predicate logic takes the ideas of propositional logic and builds on them with some new concepts that give us access to more logical tools, basically. So in order to motivate this transition into studying predicate logic, let's look at the example of a thing called an argument. All birds native to North America, which I'm going to abbreviate as NA, can fly. This is true. Flightless birds that used to be native to North America died out a long, long time ago. So all native North American birds can fly. The turkey is a bird. Turkeys are native to North America. Can we conclude anything from this information?
The turkey can fly.
That depends on what system of logic we are working with. If we are just working with propositional logic, then in fact Ibrahim is correct, which is that with propositional logic alone, you can't really conclude anything from this. It doesn't contain the tools, but it does seem like we should be able to conclude that turkeys can fly. Does that make sense? We should be able to conclude that. So in order to make that conclusion from this set of what are called premises, oopsies, sorry, that was a mistake. In order to conclude, therefore, turkeys can fly, we need what's called predicate logic. Okay, it's going to expand on the ideas of propositional logic to give us structures that allow us to make conclusions based on previously assumed facts called I just said it. What was the word I just used? Premises. There we go. Let me write that word down. These are called premises. And this would be, the conclusion. Okay. So what is predicate logic? Let's start with the definition of a predicate. So a predicate is what's called a propositional function, P of X. Like with functions in algebra and calculus classes, we use different possible letters. Traditionally, we use capital letters for predicates, okay, or otherwise known as propositional functions, kind of the same thing. And I'll use these terms predicate and propositional function pretty much interchangeably with each other. P of x, okay? We could have P of x, we could have Q of x, we could have R of x, we could have A of x or B of x or C of x or whatever letter we want to use to represent different things. So in all these cases, the idea of a propositional function is the input is x, a member of some domain. This could be, for example, numbers, people, birds, colors, etc. Like, there's a lot of different things that you could make propositions about. You could make statements about things, and so your domain is just whatever type of thing you're talking about, right? Your domain can be narrow. You could say the domain is birds, or your domain could be very broad. Your domain could be all living creatures or all living organisms, if you want to include like plants and fungi and stuff. Or your domain could be super broad and say the domain is all things. You know, like you can kind of be and depending on what you choose as the domain for the context, you might express statements in slightly different ways. We'll get to that in an example soon. So that's what x is. Now it's the input. Now the output of a propositional function is always a truth value, T or F. That's all. And the way that a propositional function is defined is by stating some proposition about x. So an example of a propositional function is something like, you might say P of x and then a colon. I use a colon usually to define a function or a proposition of any type. P of x, x is a bird, something like that, you know. And sometimes I put quotes around it. I'm not quite sure why I do that. I don't think I need to do that. So x is a bird is an example of a proposition. This can be applied to various different x's. If this is our P of x and we do P of Tristan, the answer is, the output of that would be false. P of this coffee mug is also false. P of that cardinal in my backyard, output's true, and so on. That make sense? So we have introduced the idea of a variable that comes from some specified domain and a propositional function that takes in that variable and spits out the truth value of some statement that defines the function when applied to that particular value, that particular element of the domain. Okay, so let's export this. Okay, new page. Now, what about quantifiers? Quantifiers. Let's look at some examples. P of x for x equals Tristan. This part is a quantifier. P of x for some x. P of x for all x, or for every x, which would mean the same thing. All, every, any. Those basically all mean the same thing. P of x for exactly 1 or exactly 2 x or whatever. These are different ways of quantifying a predicate. It's the way of saying, like, okay, the quantifier is like saying how many and maybe which elements of the domain is this predicate applied to. Okay. So if our, if in this context we're talking about P of x being x, it's a bird, right? If we're still using that example from earlier, then this might be P of x for x equals Tristan is false, because Tristan's not a bird. But P of x for some x, this basically means, so I want to clarify the meaning of this for some here. This means like at least, for at least one. From the domain. So assuming our domain is, we never really stated what the domain is here. Let's say the domain is all living organisms. So it includes things like birds, but also me and plants and trees and whatever. Okay, so saying P of x for some x means that there's at least one member of the domain for which P of x is true. Well, that would be true because birds are included among all living organisms, and for any particular bird you might pick, P of x, P of that bird is true, right? So this would equal true here. Now, P of x for all x is only true if the predicate is applied to any, like every element of the domain is true, right? So so P of x would be false in this statement, because not every living organism is a bird. There's you can provide a counterexample. In fact, one possible counterexample is me. I'm a counterexample, right? Tristan is not a bird, so I wish I was a bird, but I'm not. So I provide a counterexample to show that not every living organism is a bird. P of x is not true for all x, right? And then exactly 1 is also false, because you can demonstrate that this, you can say, look, here's a bird, here's another bird. There's more than one bird, right? So what happens is when you quantify a predicate, it becomes not just a function, but now a proposition. Okay, so so we can say P of x is a function, but P of x for, some x is now a genuine proposition which has a truth value. Okay, so I feel like I'm not explaining this super well, but my point is that P of x by itself is a function. It's not a proposition, it's a propositional function. It needs to be given an input in order to produce a truth value, and the truth value could depend on the input given. So P of X by itself is not a valid proposition. It doesn't have a defined truth value. But if you quantify it, this is an example quantifier here. If you quantify that predicate, then the resulting statement is now a valid proposition. It has a defined truth value. So that is the role of that is the result of combining a quantifier with a predicate. Together, they make a valid proposition. Okay, early in the semester, like on the first day of class, I gave you guys the example of like x plus 5 equals 7. That is not a valid proposition. But x plus 5 equals 7 for every real number x is a valid proposition because it combines a predicate and a quantifier. We have the predicate, x plus 5 equals 7 is a predicate, and we have the quantifier for every real number x. What is the value of this?
Two. False, yeah.
False. X plus 5 equals 7. X plus 5 does not equal 7 for every real number x, right? So, okay. So, predicates and quantifiers. All right, so let's practice. Let's practice. Let's go back to our statement here. All birds native to North America can fly. Let's just look at that particular statement. We're going to get back to talking about like the argument and then the conclusion you make based on that argument. Like we're going to get back to that like later this week, okay? But for now, let's just focus on this first statement. All birds native to North America can fly. Okay, the word all is a quantifier. Okay. Let's use the domain. Oh, hang on a second. Let me just rephrase this. This is one way to write it, but let's write it another way. I'm going to write it for all birds if they are native to North America, then they can fly. Okay, so this is an alternative way to say the exact same thing with the same meaning. All birds native to North America can fly. All birds, for all birds, if they are native to North America, then they can fly. So this statement, although it is not written with an if-then, it is sort of a disguised version of an implication statement. It has an if-then sort of implied in it. So if you're trying to express a statement like this symbolically, it can help to first rewrite it in the form of an if-then. And then we can start to convert it to something symbolic. So let's establish a domain. Let's start with just the domain birds. All birds. So now what we're going to say is for all x in our domain. Okay, so for all x, if x is native to North America, then X can fly. Like that. And now we turn this into symbols. Okay, so I neglected to introduce notation. I realized going back here, I introduced some different proposition, some different quantifiers, but I neglected to introduce notation for them. So I got to do that. Shoot. Okay, so for all X, this is our quantifier here. Oops, shoot. Quantifier here. This is denoted with an upside down A, like that, followed by X. So that upside down A means for all. And this for all X, this symbol, this combination of two symbols, I guess, that is, that's the quantifier, and it then is generally followed by a pair of brackets or parentheses, because whatever statement about X that it is quantifying, like the predicate that it's quantifying, you want to put it in parentheses so that you know the scope. A really good analogy for this is in programming, you establish a variable, and that variable is valid within a scope, right? That's what the parentheses or brackets in my case here are doing, right? I think that you can think of it like this. When you say for all X, that's like introducing a variable, like initializing it, and then you want it to be that variable to be valid and quantified in that way within a certain scope. And so that's what this is for. Okay, so always follow up a quantifier like that with a like a pair of parentheses, and then we have to state the predicate which is being quantified, which is an if-then statement. If X is native to North America, then X can fly. So I'm going to introduce two predicates, actually, two propositional functions. One of them is going to be n of X, and the other is going to be f of X. And I'll put an arrow like that. So if n of X, then f of X. And that's where n means native to North America, f means can fly. Okay. So that right there is my symbolic version of that statement. Now, there are regarding notation, there's two main quantifiers that we're going to use this semester. There's more than two in general, but just, we're going to keep it simple and just stick to really two quantifiers. This one is for all, the upside down A, and then we have this one, which means for some X, or sometimes spoken, there exists X. It's the at least one quantifier. There exists an X for which blah, 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 some predicate. Okay. As an introduction to predicates and quantifiers, this is okay. Gosh, there's some details I haven't gotten to yet, but we'll get there. I think maybe we have like 5 minutes. I think maybe the last thing I want to do is just show you how you can negate a statement that involves a quantifier and a predicate. Oh, wait, no, I forgot. There was something I was going to show you here, and it involves this example. I think it is worth exploring this example just a little bit longer, because it can help us understand how the domain plays a role in the way that you describe something, okay? The way that you symbolically represent something. So this version of it here was when the domain is birds, but if we broaden the domain to be like all organisms, right? Then that changes the way you have to represent it, because instead of saying, actually, you might want to go like that and include this version is kind of really specific to birds, because instead of saying for all birds, you need to now broaden it to all organisms. You might say something like, for all organisms, and then you have to specify that you just want your statement to apply to birds. And the way you do that is to include the stipulation, like include the fact that the thing you want to talk about is a bird. You include that as part of the hypothesis of your if-then statement. So you follow it up with an if for all organisms. If they are a bird and native to North America, and then you can say, then they can fly. So the fact that you're talking about birds, that fact gets shifted from just being implicit to the domain to being something explicitly specified in the predicate. And then when you write this out in symbols, you have to introduce another predicate that means that they're a bird. So you write for all x, if b of x, which now is going to mean that x is a bird, and native to North America, like that, then they can fly. So that's what I meant when I said that the way you write it, the way you represent a statement depends on what domain you're assuming. Okay, yeah, below.
Does there have to be a parentheses or no? Does it not matter at all?
You mean
in parentheses at b of x and n of x.
Oh, do we need them here?
Yeah.
We don't actually. We can put them there, but we don't really need them there because the and does take precedence over the implication.
So do we ever need to use parentheses or no?
I mean, sometimes, yeah. There's some situations you do need to use parentheses.
Okay.
Yeah. Talking about scope of variables here, we can look at an example where the scope matters a lot. If you take, for example, there exists x, p of x, and q of x. This is not equivalent to saying there exists x, p of x, and there exists x, q of x. These two statements are not the same. One of them says there exists an x in the domain for which p of x is true and q of x is true. Whereas the second one is saying there exists an x in the domain for which p of x is true, and there exists an x in the domain for which q of x is true. But the x in question could be different in the second statement, but not in the first. So scope matters. It is important to put those brackets or parentheses. I like to use brackets just so I don't get confused with the parentheses for the propositional function. It is, it's important to use those brackets just to be clear about which parts this quantifier applies to. And then the other thing is, if you're going to be using operations from propositional logic, like and, for example, which comes, and is like a operation that's inherited from propositional logic into this system of predicate logic. If you're going to use it, you need to make sure that the thing that you are doing the conjunction with, right, the thing that you're doing the and with, it has to be a valid proposition. So in particular, if you hadn't included this exists X right here, and the scope of this one only included the P of X, then now this becomes not valid logic anymore, because the Q of X is not quantified. It's not a valid proposition if it's just a predicate by itself. You got to quantify it to produce a proposition, and then it's good. Yep. All right. Kyler said he had to go. I think he left, which is just fine. I know we're at the end of our 50 minutes. So everybody have a lovely day, and I'll see you tomorrow on campus.
Have a good day.
Thanks, Cameron. You too.
Have a good day.
Yeah. Oh yeah. Thanks, Ibrahim. I fixed it. I put it back to being. Oh no. Sorry. No, never mind. No, that not equals, that not equivalent sign is still valid. Yeah, these aren't equivalent to each other. Whether I quantified it or not was sort of a separate point I was trying to make about that. The thing that, so whether you quantify it or not makes it valid or invalid, like a valid or invalid proposition. But even if they're both valid propositions, like properly quantified, these two statements are not equivalent. And that's because of the difference in how they are quantified and the scope of each quantifier. Do you want an example of that? I don't have to give it. I think maybe I'll give an example tomorrow, because I think it'd be valuable for everyone to hear that. Trimist.
Yeah, hello. Can you hear me?
I can. Who am I talking to?
So I'm UL. I've been
UL.
missing class recently. I think all of last week, pretty much. I just wanted to let you know. And like,
Yeah.
Is there anything that I need to make up? Because honestly, it's my fault, for missing class. I was just being